To get the most out of the Classiq platform, it's very helpful to understand its concept of operation. Let's dive into this a little bit. The most important job of the platform is to generate quantum circuits that can efficiently run on quantum computers or simulators. This process of generating a circuit, sometimes called circuit synthesis, takes two main inputs: a high-level functional model and a list of constraints. The high-level functional model tells the system what the person designing the quantum circuit wants to achieve. It specifies functional blocks that need to be implemented and shows how these functions connect to each other. For instance, a functional block might initialize several qubits to represent a Gaussian distribution, or perform a Grover search with specific oracle, or perform a math function on the output of previous blocks. The constraints tell the Classiq platform what is important to the designer. For instance, a constraint might be that the circuit should not use more than 20 qubits, or that it should use a particular set of native gates. The Classiq platform then takes these two inputs, the functional model and the constraints, and searches a huge design space to find a solution, a low-level quantum circuit. A low-level quantum circuit that delivers the functionality while meeting these constraints. During this process, the platform might examine millions upon millions of options until it finds a solution if one can be found. If the constraints change, such as when moving to a different type of computer, the synthesized circuit will likely be different. In short, the user of the platform specifies what he or she wants to achieve, and the platform finds how this can be done. We believe that this approach has several important benefits, including as the number of qubits increases, the Classiq platform can generate circuits that would be impossible to generate using existing lower-level programming tools. This approach of separating the functionality from the implementation provides a certain degree of future-proofing, ensuring that one would need to perform very little work to move from one hardware platform to another. And because the platform searches numerous options, it is often able to find solutions that are more compact than naive implementations, thus allowing the fitting of larger problems into existing computers.